Today's notes are going to be on the fundamental theorem of calculus part 1. So fundamental theorem of calculus, a lot of times they abbreviate this, you'll see it as FTC. And if you're writing on the AP test, you can say FTC. And there's two parts, so this is FTC part 1 today. Before I tell you what the theorem states, so far when we've been doing an integral, like an antiderivative, we've been changing this into like a rectangle and getting this whole entire area. And that's a Riemann sum. But as we stated before, that's an approximation. This is just an estimate. What we're really looking for is we want this exact area, and they say under the curve. What under the curve means is just below the curve. So I would want that exact area. And FTC part 1 is going to help us do that. So with that, what this fundamental theorem states, fundamental theorem of calculus states, is that if we take the antiderivative at this point A and the antiderivative at this point B, and we plug them in, that's going to kind of give us, so this is the antiderivative at the end, so like capital F of B, right? If this graph was lowercase f of x, then we plug in for x the endpoint, and then over here f of a, and if we subtract those, it gives us that area. So this area is basically equal to the antiderivative evaluated at b minus the antiderivative evaluated at a. And so that kind of gives us this fundamental theorem of calculus, which is that if a function is continuous, it does have to be continuous on the interval from a to b, then this antiderivative, the integral, is equal to f of b minus f of a. So copy that down. This is like our fundamental theorem of calculus part 1. We will be seeing part 2 next lesson. And now notice on this, we don't have to write plus c. There's no plus c here. And the reason for that is that when you evaluate this, basically you would get f of b plus c minus f of a plus c, and if you distribute the negatives, you'll notice that the c's cancel out. So when you're doing a definite integral, and remember a definite integral is with endpoints, so if we had integral of f of x dx, right now it's indefinite. Once I add in the endpoints, it's definite. You don't need to do plus c. So let's do a couple examples. The first example, we're going to do the integral from 1 to 2 of x squared dx. And basically we're going to, if we need to rewrite it, we'll rewrite it. But once we take the antiderivative, once we integrate it, we get x cubed divided by 3. And instead of writing plus c, we're going to just say we're evaluating this from 1 to 2. And this is just a shortcut notation, so you don't have to write like, x cubed over 3 at f of 2 and f of 1. Instead of writing that, we'll just use this notation here. And what that tells us to do is we're going to plug in 2. So 2 cubed over 3 minus, and then we'll plug in 1. And that gives us 2 cubed is 8 thirds minus 1/3, and so we get 7/3. And that's our exact, that would be the area under the curve of this integral. This is going to be, basically our exact answer, whereas if we had done it with a Riemann sum, it was an approximation. So a second integral for this would be the integral of 3 radical x minus 2 dx. And before you take the integral, you always want to rewrite these. So I'm going to just split it up into 3 integral from 1 to 4 of radical x minus the integral from 1 to 4 of 2 dx. And so what I did is I just split the 2, and then I brought the 3 to the outside. And technically, if you want to bring this 2 to the outside as well, you can. And so you just have minus 2 times 1 the integral from 1 to 4 of dx. Now when we do the integral, for this first one, I'm going to leave the 3 outside. And actually, I may even, before I integrate, you may want to change that radical x to x to the 1/2 power. So remember, power rule, we're going to add 1 and then divide by that 1/2 plus 1. 1/2 plus 1 is 3/2. So this is x to the 3/2 divided by 3/2. And instead of writing divided by 3/2, you can make that 2/3. And then this is from 1 to 4 minus 2. The integral of just dx is, think about this as x to the 0th plus 1 over 1. That's why this is x to the first power. So anytime you just have dx, it just becomes x from 1 to 4. And now we can just plug in. If you want to, you can simplify these. So we could actually take out this 3. And if you want to move any constants outside, you can. You don't have to. It doesn't matter. So this first one on the left will become 2 times 4 to the 3/2 power minus 2 times 1 to the 3/2 power. And then we're going to subtract this from 2 times 4 minus 1. So 4 to the 3/2 power is 8. 4 cubed is 64. The square root of 64 is 8. So this is 2 times 8. 1 to any power is just 1. So minus 2 times 1. And subtract that from 2 times 4 minus 1 is 3. That gives us 16 minus 2 minus 6, which is 8. So this integral gave us 8. Okay, alternatively, some people don't actually split these up. They just kind of do everything together. You can do that, but if you're interested in doing that, talk to me in class.